In this video, we're going to look at parametric equations. The vast majority of equations we've looked at in the past have been in Cartesian form. An example might be y as a function of x. So we could have had y is equal to x squared, y is equal to 2x minus 1. We've also looked at other Cartesian equations. For example, x squared plus y squared is equal to 25. That's the equation of a circle. With Cartesian equations, we have two variables, and it's usually x and y. With parametric equations, we have a third variable which we call a parameter. So for example, our parameter might be t or it might be theta. If it's t, we can say x is a function of t and y is a function of t. So let's look at a couple of examples. So I might have a pair of parametric equations and x might be equal to 2t plus 1 and y might be equal to 3t squared minus 4. So these now are parametric equations. X is a function of t and y is a function of t. T might be the time in seconds. If we look at another pair, x might be equal to 3 cos 2 theta and y might be equal to 2 sine theta. So again, we have parametric equations now where theta is our parameter. X is a function of theta and y is a function of theta. Many situations in physics can be modelled by parametric equations. So let's draw something up. Let's have a look now at a tennis serve, for example. If we have a tennis serve, and what I'm going to do is just draw a quick sketch. We might have now a tennis player who releases the ball from a height. Let's say the height is going to be 2.5 metres. So let's just say this height is 2.5 metres. What we could do is use parametric equations to model the path of the ball. So when they serve it, it's going to do something, give or take, like so. So this right here is going to be the displacement in the x direction, and then we'll have the displacement in the y direction. Now what we could say, let's just say this had a speed now of 15 meters per second. So let's say this is going to be 2.5 meters, and let's say now had the initial velocity 15 meters per second. What we could look at now is a path that this ball is going to take. So if we look at the horizontal displacement, we could say that x was equal to 15t, where t is the time in seconds, and y would be equal to 2.5, which is the starting height, minus 15t squared. So this now gives us an example of where parametric equations could be used to model the flight of a tennis ball. So if we look at this now, quite clearly we would have to define a certain range of values of t that we could actually use. We don't want to make this, for example, 600, because quite clearly it's not going to be valid for 600 seconds. So what can we get from this information? Well, we could think about the time now that the ball hit the ground. So let's think about this now. If that's the case, when did the ball hit the ground? Well, that's going to be 0. So we could say 0 is equal to 2.5 minus 15t squared. So t would be equal to the square root now of 2.5 divided by 15. So let's put that through a calculator, and now we could say 2.5, so 2.5 divided by 15. So that's going to give me now root 6 over 6. So that's the time now when it's hit the floor. Of course, from this we could then get the displacement in the x direction by simply multiplying this by 15, and that would tell us now how far it's gone in this direction. So as you can see, so that's going to be 6.12 meters. I mean, I've just chosen these aren't massively realistic, but it'll give you some idea on how these parametric equations can model real life situations. What we're going to do is just do some basic work now, and we're going to start with graphing some of these parametric curves. Now some of these give rise to really nice curves. What we're going to do is just start off with a basic example. So let's get up something. Let's say let's go for x is equal to, let's say 2t squared, and then y is going to be equal to 4t. And let's take now t, we'll say that t, we will define t to be from negative now to positive 3. Okay, let's go ahead and now put a little table up. So what we'll have is our table. We will have a value of t, we will have a value of x, and we will have a value of y. So what I'm going to do is put in here t, and then I'll have x, and then I'll have y. So we'll start with t is minus 3, we'll do minus 2, we'll do minus 1, we'll do 0, we'll do 1, we'll do 2, and we'll do 3. So if we consider now subbing in, and I think I'll plot this as I go. So let's go ahead and do this. So what we'll have then, our Cartesian axis, we'll have the x and y axis. This is going to be x, and this really will be a sketch. I'm not going to plot as such, it will just be a sketch. So what we've got then just here, that'll be 0, and then we've got x increasing and then y increasing. So if I sub this in, if I square t, that'll give me 9, 2 lots of 9 is 18. If I now put in here minus 3, when t is equal to minus 3, that's going to give me minus 12. If I take t to be minus 2, if I square that, I'll get 4. 2 times 4 is 8. If I sub this in, I'll get now minus 8. If I sub in minus 1, that'll give me 2. That'll give me minus 4. I'll get 0 and I'll get 0. So all I'm doing now is feeding t into now my parametric equations to plot this curve. So if I put 1 in, we will get 2, and then we will end up now with 4. If I sub in 2, I'll get 8, and I'll get positive 8. Hopefully now you can see the symmetry appearing in this. So if I now sub in 3, if I put in 3, I'm going to get 18, and I'm going to get 12. So let's have a look at this. Starting here, what we're going to have is the following. That's going to be 0, 0. Now, we could, if we wanted, do this starting at minus 3. If I started at minus 3, and let me just really sketch this, what we're going to have, 18 is going to be here, and we're going to have minus 12. I could on here now show that this is t is equal to minus 3. When we're plotting these, often we'll put the value of t on. So if we take now minus 2, we can see this is going to be curving round this way, and I'll show that now with arrows. So when t is minus 2, we've got x is 8, so let's say that's about there, and then we've got now that y is minus 8. So let's say that's approximately give or take there. So that's going to be 8. I know this isn't hugely accurate, but hopefully it gives you some idea. So let's now put on here that t, so this is the point where t is equal to minus 2. And then if we consider when t is equal to minus 1, we'll have 2 and then minus 4. And it'll look something, again, give or take, like so. So that'll be just there. So we'll have now this point when t is going to be equal to minus 1. Then we got 0, 0, okay, and we'll plot that point there. So this is the point now, 2. And then you can see by symmetry when t is 1, so let's put here t is 0, so t is 0. T is going to be equal to 1, that'll be just here, and we'll have that one. Then when t is equal to 2, we will be just here, and then when t is equal to 3, we'll be up here. Now, as we can see from this, we're going to end up now with a parabola. So we can draw now this parabola, and it'll look something like so. This is meant to be symmetric, but you get some idea. Now we can show that t is increasing by the arrows pointing in this direction. So when I'm tracing this curve out, I can show now that t is increasing now from the left up to now the origin, and then we're going right in x increasing. Now, as you can see, this is giving me this parabola which is sitting on its side. If we look at these equations now, we can do something called eliminate the parameter. It's not always possible with the parametric equations, but often we can either use algebraic manipulation or trig identities to actually get y as a function of x, or at least put this in Cartesian form and eliminate the parameter. So let's go ahead and try and do this. So if we consider now that we've got x, and I'll write them down here, let's just scroll down a little. We've got now x is equal to, and it's 2t squared. So 2t squared, and y is equal to 4t. So let's consider making t the subject with this one right here. We can say, therefore, y will be now over 4 will be equal to t. So what I've got now, I've made t the subject. If I sub this in here, I can say that x is equal to 2 lots of y over 4 squared. So that gives me that x is going to be equal to now y squared over 8. So I can say now that y squared is equal to 8x. And this now gives me here, instead of y as a function of x, we've got x as a function of y. And this gives us a parabola. And we can say this will look something like so. And in general, we can say this is y squared is equal to 4ax. And that now is a standard parabola that's sitting on its side. So as you can see from this now, I've eliminated the parameter. So if you're asked to convert this into Cartesian form and eliminate the parameter, that's what I've just done here by making t the subject of one of the equations, by algebraic manipulation, and simply subbing it in. As you can see, by doing that, I may lose some information. So for example here, if I've eliminated t, I can't tell at certain times where the ball is. All I've got is x and y. So we need to be fairly careful of that. Also, if we eliminate the parameter, there's also the issue of knowing which way, for example, if this was a particle, which way the particle is travelling. But as you can see, we can go ahead and eliminate the parameter. It is also generally a lot easier to switch this from parametric to Cartesian than the other way round. So let's look at just eliminating a parameter or two. Say we had some parametric equations, x is equal to 5t and y is equal to, let's go for 5 over t. Now if we look at this now, I can make t the subject on this one right here. So I can say that t is equal now to 5 over y. Simply subbing that straight in, we can see now that x will be equal to 5t. Well, t is 5 over y, so we're going to have 5 lots of 5 over y. And that gives me now that xy is equal to 25. And this is in the form xy is equal to c squared, which gives us, and we wouldn't be expected to know this, but this gives us a rectangular hyperbola, which looks something like so. So if we looked at it the other way, we could say that y is equal to 25 over x, which might be more familiar with you if you haven't done any other curves. So what I've done, I've taken this now from parametric form, where I have a pair of parametric equations. I've eliminated the parameter t and expressed this in Cartesian form. Okay, let's have a go at something else. Let's go on and let's write some other parametric equations. So let's say now that x is equal to 2 cos theta, okay, and y is equal to 2 sine theta. So let's start with something nice and straightforward. Now what we'll say then, we'll take theta and we will go from 0 and we'll go to 2 pi. So what we'll have is theta from 0 to 2 pi. Now I'm going to draw up a little table. What I'm going to do enough values in here, hopefully, for you to see what's going to happen with this. Okay, so what we'll do, we'll have theta. So theta is going to be just here, and we will have now x, and we'll have y. So what I'll do, I'll start with 0. I'll certainly do pi by 2. I'll certainly do pi. I'll certainly do 3 pi by 2, and then we'll look again at 2 pi. When we get 2 pi, hopefully we'll see that it gives the same value right here as 0, but I'll bolt it on at the end just now to have that there. So what we can have from here is the following. Let's just put these up. I might put some values in the middle just to make this more obvious of what it's going to do. So hopefully now, in fact, I'll just draw some sine and cosine curves. Let's just familiarise ourselves with these. So if I just draw them just here. Let's draw now the cosine curve. Cosine curve from 0 to 2 pi will do something like so. Okay, and then the sine curve will do something like so. So this right here for cosine is going to be 0, 1. We've got now pi by 2, 0. We've got this point right here, and this point is going to be pi, minus 1. This is going to be 3 pi by 2, 3 pi by 2, I'll manage to get that out. And then this is going to be 2 pi, 1. For sine, we've got now 0, 0. We've got pi by 2, 1. We've got pi. We've got this point, so pi 0. We've got this point, which is 3 pi by 2, minus 1, and then we've got 2 pi, 0. So if we consider now, if theta is 0, right here I'm going to have x is 2 lots of cos of 0, so that's going to be 2. And then sine of 0 is 0, that's going to be 0. If I take pi by 2, cosine of pi by 2 is going to be 0, and now sine of pi by 2 is going to be 1, so that's going to give me 2 lots of 1. Okay, if I now take the cosine of pi is minus 1, 2 lots of minus 1, that's going to give me minus 2. If I take now sine of pi is 0, so that's going to be 0. If I now take this one right here, 3 pi by 2, cosine of 3 pi by 2 is 0, and then the sine of 3 pi by 2 is minus 1, so that's going to give me now minus 2. And then of course we can see this is just going to be replicated. So what I'm going to do is just sketch this up. hopefully now you'll see what we've got. We've got our x and y coordinate axes. So this is going to be now x, so that's going to be y, and this is going to be x. Okay, I've traced it out from here back round this way. So if I consider now the following, when I put theta was 0, x was 2, y is 0, and that's just there. That is 2, 0. When I subbed in pi by 2, we saw that x was 0, y was 2, and that's going to be just here, 0, 2. When I subbed in pi, we had now minus 2, 0, which is going to be just there. And then when I subbed in 3 pi by 2, I got 0, minus 2. Now, of course, we can keep going round. And if we just think about this now, if I picked, and let's just see if I can squeeze in here, pi by 4, that's going to give me, if I rationalise this, root 2 over 2 for cosine. So I'm going to have 2 lots of root 2 over 2, and for sine, I'm going to have 2 lots of root 2 over 2. The sine and cosine of pi by 4 is root 2 over 2. So this is going to give me this point right here, root 2, root 2. Now, what I would see if I continued to plot points, I would end up now with a circle. Okay, and that would be a circle. We can see that the radius on here, if we look at this, is going to be 2. What I'm now going to do is eliminate the parameter right here using a trig identity. Now, we know that cos squared theta plus sine squared theta is given to be 1. So, if I now look at this, I've got x over 2 is equal to cos theta. I've got now y over 2 is equal to sine theta. Therefore, if I square each of these terms, x over 2 all squared plus now y over 2 squared will be equal to 1. If I multiply through by 4, x squared plus y squared is equal to 4. Now, we've seen this before. This is a centre circle, 0, 0, and a radius now of 2. And we can see quite clearly in parametric form, I've shown that by plotting the points. So if I wanted, I could now show that I'm essentially drawing this out in this direction, and I could put my values of theta on this. So theta is equal to 0, theta is equal now to pi by 2, theta is equal now to pi, theta is equal to 3 pi by 2. So there we go. I've traced out now, this is an example of a pair of parametric equations. X is a function of theta, y is a function of theta. I've gone ahead, I've sketched it out, then I've eliminated the parameter using trig identities and just gone ahead and shown something that we've seen time and time again. So let's have a go at eliminating some parameters. Let's go for something slightly different. Let's say I've got x is equal to, let's go for 3 cos theta, and y is equal to, let's say this is going to be 5 sine theta. So again, I can say from here the following. I can say x over 3 is equal to cos theta. I can say that y over 5 is equal to sine theta. Therefore, if I square them using this identity, which I will quote when I'm in an exam, we've got x over 3 squared plus y over 5 squared will be equal to 1. This gives us now an ellipse, and you'll come on to looking at ellipses if you take your work any further. If we looked at another one, for example, using yet another trig identity, we might have, for example, x is equal to 4 sec theta, and y is equal to, let's go for 3 tan theta. So I know that sec squared theta will be equal now to tan squared theta plus 1. Therefore, I can say x over 4 squared will be equal now to y over 3 squared plus 1. And we can rewrite this now as x over 4 squared minus y over 3 squared will be equal to 1, which gives us a hyperbola, which will look something, give or take, like so. So that again shows we can eliminate the parameter using a trig identity. In later videos, we're going to look at differentiating and integrating parametric equations. We'll do a brief intro now. So what we see now, for example, x could be given as a function of t, and y can be given as a function of t. To differentiate, we've got two choices. The first choice is that we convert this into Cartesian form and simply write dy by dx is something. Alternatively, we can use the chain rule. We can use results from a chain rule to differentiate and integrate now these parametric equations. So using the chain rule, we can say dy by dx will be equal to dy by dt multiplied by dt dx. And that now is the chain rule which you will have seen time and time again. So let's just pick something now. Let's just say, let's go for x is equal to t squared plus 1 and y is equal now to 3t minus 6. Okay, now the way I like to do this, despite this being less rigorous, I like to write 1 over the derivative of x with respect to t and multiply it by dy dt. So let's have a look at this now. So we can say dy by dx will be equal to dy dt. So if I differentiate y with respect to t, that's going to be 3. I now need to multiply this by dt dx. Now from here we can see that this will give me, if I differentiate x with respect to t, I'm going to get dx dt will be equal to 2t. Therefore dt dx will be 1 over 2t. So if you look at what I've just essentially said, is that if we do 1 over the derivative of x with respect to t and multiply it by the derivative of y with respect to t, we would end up with what we wanted. So another example, x might be equal to, let's say we've got sine theta, and y would be equal to, let's say we've got 2 cos 2 theta. So if I want dy by dx, I want dy by d theta multiplied now by d theta dx. So informally, I can simply do 1 over now the derivative of x with respect to theta. So we can say dy by dx will be equal now to 1 over cos theta multiplied now by the derivative of 2 cos 2 theta, which is going to give me minus now, and we're going to have 4 sine 2 theta. So I could write now dy by dx would be equal to minus 4 sine 2 theta over cos theta. And whilst we're here, we'll look at something that they might ask us to do. They might ask us to write this in a certain form. And if we consider this now using the sine 2 theta, let's write this here. Sine 2 theta is equal to 2 sine theta cos theta. We could write this now as minus 8 sine theta cos theta over cos theta. So they might ask us to show that dy by dx is equal to minus 8 sine theta. And then of course you would be given values of theta at a certain point on a curve to evaluate the gradient and potentially find a tangent to that curve. So there we go, that's differentiating. Again, by the chain rule, we can use integration. So we can integrate. And what we can say is now, it's if we're integrating parametrically, we can use now y dx dt dt. So what we'll have now is the integral will be y dx dt dt, and we'll just have t1 and t2. So we'll be either given or we'll need to find these limits. So for example, now let's say we had, let's go for something, let's say we had x is equal to, let's pick something t squared, let's say t squared plus t, and let's say we had y is equal to, let's go for 2t minus t squared, so 2t minus t squared. So in this particular case, we might now be told we're going, we want the integral, and we might have t1 we found to be, for example, 1, and t2 we found to be 2. So all we would do now here, we could say that the integral I would be equal to now. So what I want is dx dt. So from here, we would say now dx dt is going to be 2t plus 1. So we're going to have now the integral, and we'll go from now, we'll have 1 to 2, and then we will take now this value right here. So that's dx dt. So we've got 2t plus 1, and we're going to multiply that now by 2t minus t squared. So 2t minus t squared, and now we're integrating this with respect to t. So this would just be a simple integral from here. We would now go ahead, just multiply this out. Let's do that. Let's just expand this out. 4 t squared, then we're going to have minus t squared plus 4t squared, which is going to be plus 3t squared. And let's just, sorry, t cubed, my apologies. Let's do, in fact, let's actually, rather than me trying to talk my way through it, let's just actually expand the damn thing. Let's go ahead and do that properly. So if I do that, I'm going to get now 4t squared. I'm going to get minus 2t cubed. Then I'm going to get plus 2t and minus t squared dt. So let's go ahead and check I've got all of that. So if we consider now I will be equal now, and we're going to evaluate. So what have I got here? I've got 3t squared. So if I integrate 3t squared, that's going to give me t cubed. So 4, I'm not doing a good job of this, am I? 3t squared is going to give me t cubed, isn't it? And then I'm going to integrate this one, which is going to be minus 1. What we can have 1/2 t to the 4th, and then we can have plus t squared. And we'd be interested in that from 1 to 2. So as you can see, I'm kind of losing my way a little doing this integration, but it's straightforward integration, and there's plenty of different videos on that. In later videos, we will look at this, but the take-home message now is that you're multiplying y, which is just here, by the derivative of x with respect to t, and you're integrating with respect to t between the limits that you've either found or converted them. So again, with this, you could put it in Cartesian form, or you could put it in Cartesian form to check. With both differentiation and integration, we have the choice. Generally speaking though, we will integrate with respect to t, or we'll use the chain rule rather than converting to Cartesian form. So there we go, an introduction to parametric equations. I'm a little disappointed with my inability to expand a pair of double brackets, but hey ho, it could be a lot worse. So the take-home message is, essentially a Cartesian equation has two variables, generally x and y. Parametric equations have now a third variable called a parameter. Often that's given as t or theta. We can eliminate that if we like, or we can leave it in parametric form. We can sketch these, we can differentiate, and we can integrate them, and we can look at a whole host of different applications in the real world. So this is the first video done. We will go on to look at some more in later videos.